Hi guys, here's my Honda QA50 that I'm fitting a Sachs KM48 rotary engine into. The final piece of the driveline left to do is this toothed belt. Some people call it a Gilmer belt or a timing belt. Got these steel blanks here that I purchased from Auckland bearing distributors. They're an 8M, which is an 8mm pitch. They're 50mm wide. I've had this belt cut specially for me. It's a 760mm long belt. So these steel blanks are super heavy. Off the shelf, weighing in at 2,269 grams. So right on 1 pound. So I decided to set about boring some of the weight out in the lathe. Here you can see me putting a pilot bore through, 18mm. The final shaft size is 19mm or 3/4 inch. I leave that bore till last. For now I'm just roughing out a whole lot of weight. So here it is after I've finished boring it. Managed to shed around a full kg, so down to 1,261 grams now. Alright guys, so you've just seen me bore those pulleys with this boring bar. This one's too big to do the 3/4 inch bore that I need to do to fit it onto the bike. You can see there that it's around 19mm, which is 3/4 inch. So that's the size that I need to bore to. So what I've done is I've gone and picked up a smaller boring bar from Machinery House. It's a S12M. It's code there LO21. Now this one here measures around 14.2, which is 9/16 of an inch. So that's going to be a much better suited bar for boring the 3/4 inch bore. So these take a little cemented carbide insert, sintered rather, perhaps. It's actually compressed powdered carbide, tungsten carbide that is, and it's compressed and then heated to an extreme temperature, which allows it to take that shape. And I believe they're actually ground after the fact, and that's coated with a titanium coating, which is that gold coating. It's a titanium nitriding process, so it's a vapor deposition process. Improves the wear, basically, the wear resistance of the surface. So when we install these inserts, we've got a very small Torx screw there. Take that out. Being a nice new bar, I don't need to worry too much about cleaning out this, what's called the seat. It's in quite clean shape. I'll give that a little blast with compressed air, just to make sure there's no debris under there. Just give that a wipe with my finger first. All right. See how that sits in there neatly. Pretty fiddly little screw. Alright. Now they give you these little tools. They don't have much leverage. That's for a reason. They don't need to be super tight. Check it's engaged properly first. Nice little nip. That's that. So we'll go and set that up in the lathe now, and I'll show you how I bore that 3/4 inch bore accurately to size. I'll show you guys how to quickly true something up. So when we put a job like this in the chuck, it's not uncommon for it to run out slightly. And typically the run out's not so much in the jaws, although with a 3 jaw it's not always perfect. quite often it's just that it's grabbed in the jaws slightly crooked. So by using a clock gauge, well, clock gauge is a nickname, it's actually a DTI or a dial test indicator, we can easily see the run out and we can see how to adjust it. So we can pull back on the plunger like this to pull the needle off the surface. So I can see the high point there. I turn it to the low, pull the needle off the surface so that I don't transfer any shock through to it. Just give it a little tap and then check. Nailed it in one hit. That's within 0.01 of a millimeter, which is really good. So we'll leave it at that. Not always that easy. So I've mounted my new boring bar into this quick change tool post holder. I'll show you how that works. So these are a machined block with accurate mating surfaces here. They basically engage on there, and then when you twist this to lock it, it pulls back a little plate which pulls the whole thing hard against the tool post. So it allows you to change tools quickly and accurately. So I've got a little adjuster screw here, and the reason that's there is to set the center height. So what we do is we just adjust that screw. When you lock it up, it just sits down on it. Every time you put the tool in, it goes to the same height. And the center height is important because if it's not in the center of the bore of the machine, whatever it is that you're boring, then you're not going to get an accurate measurement. Whatever you wind on your dial isn't going to correspond to the actual cut that you take. Alright, so I'm ready to start the spindle. I'm going to run it at 700 RPM. I'm going to bring the bar in manually and just touch it on the inside. That's going to give me my base starting point. I'm going to set the DRO. I'm going to proceed to take some passes. Very fine. I'm going to stop. I'm going to measure it with a micrometer. I'm going to readjust my DRO appropriately, depending on what that measurement is from the micrometer. And I'm going to continue. I'm going to take my finishing pass. Here's what I'll be using to measure the inside of the bore. It's called a telescoping gauge. These ones are made by Michitoyo in Japan. A few different brands available on the market, but these have served me well. I've had these since I was an apprentice. Engraved with T for Tim. This is a micrometer. A lot of people will be familiar with that, some may not. It's a very accurate way of measuring. It's pretty much your go-to in engineering. You use this for measuring anything in the lathe that you want to know is within 0.01 of a millimeter, so 100th of a millimeter. If you're American, obviously this would be probably in inches, decimal inches. To give you an idea, 0.01 of a millimeter is a little less than 1/2 of a thousandth of an inch. So what I'll do is I'll put that in the bore you'll see me twist it sideways after locking the screw. Then I'll measure it with this. Right, it's a very, very fiddly, precise feel. So that reads 15, and we keep counting on, 16, 17, 18, we're not quite at 0.5, so we're at 18.45. So on my DRO, I was at 18.43, which was a pretty good guess at where we're at. So what I'll do is I'll update my digital readout to 18.45, and then I can safely take my way all the way to my finished diameter, knowing that my digital readout is set correctly and my tool is set correctly. Before I go ahead and do my finished bore, what I'm going to do is actually measure this shaft with my micrometer. Right, so that's 19.08. So it's ever so slightly over 3/4 inch. It's over by 1/1000th of an inch. So it's not ideal, but it's okay because I'm going to be boring it to suit. Now I want a very, very snug fit. I want no wobble because I'm actually working with quite a small contact area on the shaft because I've bored the inside out of my pulley. I've only got about 20 millimeters that's actually contacting the shaft, so I don't want any play in there because that will eventually over time fret away and that play will increase. So what I'm going to do is I'm going to take that measurement, so 19.08, what I'm going to do is head for 19.1, that's going to be 0.02 of clearance, and 0.02 is fairly minimal. The other shaft, which will be getting the second pulley, interestingly measures 19 on the dot. So that means it's 0.02 of an inch undersize. So I'm going to do these two pulleys and they're both going to be slightly different. Alright, so I'm going to set this at 18.45 like I said I would. So X is my in and out direction, so traversing crossways to the spindle. Y, on some machines that would be called Z, but that's traversing in and out of the spindle in the same axes. So you can see the numbers move as I traverse it towards this chuck. Right guys, so I've completed this one. I've bored it to 19.02 millimeters. So it's got 0.02 millimeters of clearance on that back jack shaft on the bike. The reason I've done this smaller one first is that if you stuff it up and you go slightly oversized, with a bit of luck you'll be able to use it for the larger one. So in this case I've got spot on. You'll notice the last cut I took was actually a repeat pass at the same 19.02 diameter. And the reason that you do that is because with a cutting tool, there's something called cutting pressure. Especially with a boring bar that's hanging out that far, as it tries to cut, the metal actually sort of repels the tool from the pressure of the cutting. And what happens is your second to last cut will still have some pressure in the tool, so it won't be cutting true to the actual diameter. So what we do on the second pass, by leaving the numbers the same, we're actually able to take out that cutting pressure and take it all the way to finished size. So here I'm just reducing the shoulder diameter down because it's unnecessarily big. Alright guys, we're going to drill the holes in here. So I've worked out I can drill 10 holes with a 12.5 millimeter drill, evenly spaced, and that will just nearly touch this and just clear the inside of here when they break through. what I'm going to do is bolt it down to the table. And I'm going to use my digital readout, which has a pitch circle plotting feature. You might have heard the term PCD when referring to a bolt pattern on a round pattern. So that's what that stands for, pitch circle diameter. So what I need to do is zero the machine in the center of this. So to do that we use our DTI again, our dial test indicator. This is a much more precision finger type than what you saw me use last time. So what I'm going to do is, with the magnetic base, I'm going to clip that onto the chuck there. It's quite a neat unit the way that works. It's a collapsible all with one knob, so you slacken that off and then the whole thing goes limp. Position it exactly where you want it and then do the knob up and it locks it in place. So what I'll do is start turning the spindle, and what I'm doing is comparing where the finger is in relation to this round boss that I want to true up to. So what I start by doing is just splitting the difference, just eyeballing it. Right, and you can start bringing it closer and closer, because this unit only has 0.8 of a millimeter of travel. So I have to get it within 0.8 before I can start to use it. Right, pretty close, bring it on. So I can set that at 0 on that side. That'll help me a bit. Come around the back and it's on 0.25. So what I can do is split the difference. Oh, went the wrong way. It's a bit hard to show you what I'm doing because you can't see the dial as it goes around the back, but what I'm doing is just registering the number and then splitting the difference until I've got it down to no error. Alright, so once the needle's stationary, as you rotate it right round, you know that you're in the 0, 0. So we can set the home position. 0, enter, 0, enter. So now that we're in the center, we can start programming the pitch circle plotting. So we go into the center position, 0, 0, say yes. The diameter I've worked out is 51.5 millimeter, so that's the PCD. So okay to that. Number of holes is 10. We're starting at 0, which is out here. You can start anywhere around the 360 degrees, but obviously we just want to start at 0 for this. And then our end angle, 324 degrees. So to arrive at an end angle of 324, all we're doing is we're saying we're putting 10 holes evenly spaced around 360 degrees. So each hole is 36 degrees apart, because 360 divided by 10 is 36 degrees. So the 10th hole is at 324 degrees. So okay to that. Now hole number 1, these coordinates here are where we need to move the table to. Once it reads 0, we're in position. So the first one's easy. It's our 0. I'll draw the first couple of holes in real time, and then I'll switch to a time lapse to smash out the rest. Goes quite quickly, but It will take me about 10 minutes. Now what you'll see me doing is a technique called pecking, where you take a small depth cut and then back off, and then back off. The reason I'm doing that is just to break the swarf so that you don't end up with long stringy swarf. You end up with smaller pieces that are easier to manage, easier to clean up, and it's a lot easier going on the drill. So you'll see me use a bit of cutting oil on there. Here we go. Alright, it's the first hole done. Turn my fan on to blow that smoke away. So we can scroll down to hole number 2. There's our coordinates. So we turn this one to 0. And this one to 0. There we go. And on to 3. Okay, let's take a look at how we're going to deburr these holes. So you see the sharp edges left from the drilling when it breaks through. So because we're so close to the edges here and in here, I've got a couple of special tools here I'm going to show you. First one's a hand deburring tool. This one's by Noga. I think it's European made. These are really common in the trade. Now this is good for doing just around there like that. Now what I can't do with this is do this half of the hole in here, because the tool would just clash with that. I can't reach through like that because it's not long enough. So here comes another special tool from Noga. It's a very interesting little 45-degree ground tool. This is on an extension arm, so you can extend it. Now let me show you what we use this for. So I can reach right through the hole with it, set it on there, and then by applying some pressure down and twisting it, I can take a shaving off all the way around there like that. That's how we do it. That's a toolmaker's trade secret. And on the inside, I can use this tool again. And run it around there. Again, I can grab this one. Take care of that half of the hole. That's how I do it. Cool, so here's the two pulleys, fully lightened. You've seen how I bored them and how I drilled them. Now let's chuck them on the scales So we started off at 2,260 grams, 917 grams. So we managed to shed some serious weight out of these. So pretty happy with that. I think they look pretty cool. They're starting to look a little bit sort of shabby. What I'm going to do is sandblast them, give the whole thing a nice surface. Then I'm toying with the idea of actually chrome plating these, or maybe just powder coating them. Alright, I've got it all just sitting on there. So I polished the shafts down until these were a really neat fit on them. I just sort of bumped them on with a mallet, so I'm really happy that there's no play in them. Obviously I haven't got the keyways in yet. That'll have to be in part 2. I've ordered a special broaching set with guides. I'll be able to do that in my hydraulic press. This is so cool. I'm really, really excited to hear this. I mean, that's a 2-inch wide belt. I think this thing's going to scream. I've got this gold guard here for Paul's bike. I just set it on there before and I really like how that gold looks on this bike. It's got a little bit of gold around the tank there. So what I'm thinking is I might do some nice gold accents on this. I want to do a guard inside here so that you can't catch your fingers in here. Obviously that'll be a bit of a widowmaker if someone gets their limb in there. Well, thanks for watching, guys. Don't forget to like and subscribe, and I'll see you next time.